Hello, everyone, and welcome to the first webinar of this year. I hope you all are doing good and have had a fantastic start to 2026. The topic of today's webinar is sphere on sphere model, shoulder model including humeral head translation. My name is Divyak Chandra and I work as a biomechanical specialist here at Anybody Technology. Today I will be the host of this webinar and I'll be joined by my colleague Morten Lund during the Q&A session in the end. In the Anybody webcast series, we host a variety of presenters who've used Anybody modeling system in different applications. In today's webcast, I'm very pleased to introduce our presenter, Margaux Peixoto, who is a PhD candidate at ETS Montreal. Margaux will present her recent work on a sphere-on-sphere glenohumeral model that combined force-dependent kinematics to simulate muscle and joint forces while considering humeral head displacements. Margaux's research is already published in Journal of Biomechanics, and you can go and check out the paper if you'd like to read the very details of her work. The presentation will start in a few minutes or so, but just before we start, I'll give a general introduction and overview of Anybody modeling system for those of you who are unfamiliar with the software or musculoskeletal modeling and simulations in general. First of all, I would like to draw your attention to the control panel. The control panel appears on the top right side of your screen. You are welcome to submit questions and comments via the questions panel during the presentation, and we will try to address the questions at the end of this webinar. In case we do not get to answer all your questions, we will try to do so by email within a reasonable time. So let's begin by having a look at what Anybody modeling system actually is. Anybody modeling system is a software that allows you to do musculoskeletal modeling and simulations. As input, it takes motion data and forces, and as output, it calculates internal body loads such as joint reaction forces, muscle activity, and metabolic energy. Anybody is used in a wide variety of areas and applications, and a few examples of these are movement analysis, product design optimization, sports optimization, orthopedics and rehabilitation, ergonomics with and without assistive devices such as exoskeletons, and in the automotive industry. The typical workflow in Anybody could look like this. You provide the recorded motion data as input and use the body models which you or others have built. And then you can optionally provide some kind of environment, which could be a special type of equipment or, for example, an exoskeleton. Then you can use Anybody to combine these things and run the inverse dynamics simulation, which solves the muscle recruitment problem. This basically means that we go from motion to calculating the internal body loads and interaction with the environment in some cases. You can then output the results and use it for post-processing with, for example, some kind of finite element tool, but many users also close the loop completely by doing some kind of design optimization and then run this cycle multiple times. This actually brings me to the end of the introduction, and I will hand over the word and presenter role to Margaux now.
Okay, perfect. So hi everyone, I'm Margaux Peixoto and I'm a PhD candidate at ETS SHIM, as Dave introduced me. And today I will share to you the work I've been doing on the Anybody shoulder model to include humeral head translation. So the point of this work on the shoulder model was to help me during my PhD to answer and to better understand a question about the mechanism of injuries influenced by the scapular and the humeral morphology. So first of all, I will introduce you briefly to the shoulder joint and the glenohumeral joint, which is the joint I'm really interested into. So you have to know that the shoulder joint is the most mobile joint of the whole human body. And to achieve like the really huge range of motion we can do, like raising the hand overhead, for example, it has to be very mobile. So the glenohumeral joint is the joint between the humerus, you can see there, and the humeral head, and the glenoid of the scapula. So this part over there. And another point of interest I have in the scapula is the acromion, because some muscle are present just after attached over there. What's interesting with the shoulder, it's very, very unstable, so to have a very high range of motion. So the stability is not really assured like the hip, for example, by the congruence between the humeral head and the glenoid. There is very low surfaces of contact. And so humeral head translations, so the humerus going upward, have been measured in vivo going up to 12 millimeters. So really, the stability of the joint is not very well assured by just the bone congruence. Okay. Because the congruence does not assure the stability of the joint, the muscle do it actively. So the calf muscle you can see over there are very, very important when it comes to the joint stability of the shoulder. So you can see over there the supraspinatus that initiate abduction, but also help to compress the humeral head into the glenoid. And on the interior parts, there is the subscapularis, and on the posterior parts, the infraspinatus and the teres minor. And altogether, those joints really compress the humeral into the glenoid to ensure that there is no dislocation. But they're very small muscles, so in order to perform abduction, the torque is produced by deltoids, so that goes all around the shoulder, and that's a very, very big muscle with large moment arm, and that's really the one that perform abduction. So the etiology of the common shoulder pathologies, such as osteoarthrosis or rotator cuff tear, is still really poorly understood. But one hypothesis is that the morphology of the scapula affects the biomechanics of the joint, with some individuals may be more prone to develop certain pathology. And so in order to investigate the relationship between the scapular morphology and common shoulder pathology, the study of Moore and the collaborator introduced a new geometrical parameter, so the critical shoulder angle. You can see the radiological calculation over there. So the critical shoulder angle is defined by the extremity of the glenoid, so there, and the lateral extremity of the acromion over there. And what they found is like small CSA was correlated with osteoarthrosis. Was correlated with osteoarthrosis. The normal joint was pretty healthy, and large CSA was correlated with rotator cuff tear. But in order to better understand the pathomechanism, musculoskeletal can be used so that we get the link between the morphology and really why it can lead to such different pathology. So as I said before, the stability of the shoulder is ensured by complex mechanism. The congruence between the glenoid and the humeral head is ensured by a really poor passive stabilization of the joint. However, it's not sufficient due to the small contact of surfaces. Therefore, the rotator cuff muscle activate to center the humeral head into the glenoid and to ensure an active stabilization of the joint. But however, most of the musculoskeletal models represent the glenohumeral joint as a ball and socket joint, so you can see there. So it's only 3 degrees of freedom in rotation. And what this means is that the humeral head translation cannot be simulated, even if they have been measured in vivo, and this results in non-physiological muscle activation patterns. Since a perfect congruence is assumed with a ball and socket joint, rotator cuff model are not required to activate in order to stabilize the joint. So to study the effect of morphological variation on the shoulder, such as the CSA, and in particular on the muscle forces, it's really limited with the ball and socket model. So we need to have a model that represents the humeral head displacement. So the main objective of my work was to develop a model that allowed for humeral head translation in order to study the relationship between shoulder bones morphology and the pathomechanism. And so the main research question was, does the morphology of the bone influence the tendency to develop a specific shoulder pathology? So in order to do that, I've been using the anybody musculoskeletal models that Dave just presents. So as input, we have the bone geometry, so the length, the mass, the inertia parameters, the muscle geometry, so all the parameters for the heel-type muscles, such as the length of the fiber, cross-section area, physiological cross-section area, max isometric forces, etc. We have the kinematics, so the motion we want to study. It can be either mocap or drivers. In my study, I'll be performing abduction, so I will just drive the arm upward. And we can add external forces, such as like a load, for example. So it's a model, and as input, we have the joint reaction force and muscular forces. But what we don't have is the specific kinematic of the humeral head translation. And so in order to do that, I look into the literature to see what has been made before. And a model that I was really interested to was the Elabashi model. It was only a kinematic model, so no musculoskeletal modeling, but they had the idea to impose a geometric constraint between two spheres. So what they have been doing is they have two spheres, a small one for the humeral head and a bigger one to represent the glenoid. And they link these two spheres with a connecting rod. So it's just a geometrical constraint. And in any body, the way to represent humeral head translation, it can be done with the force-dependent kinematic algorithm. It has been done previously for model with arthroplasty, healthy joint, and rotator cuff tear. So what the force-dependent kinematic algorithm do is that the joint positions are considered are unknown, and they're solved by requiring the static equilibrium of the joint. So the solver will iteratively adjust the relative position and orientation of each segment. So here's the humerus. Until the sum of like the muscle forces, the joint external forces, joint reaction force is close to zero. So the motion of the humeral head is an outcome of all the forces are applied on the joint and not prescribed as a kinematic. So not like with the driver, for example. So this solution is a really, really good solution to have a very nice kinematic like a nice kinematic for the humeral head. But what is not solving is that because they add additional springs, so this is the model from Thin, it was a very simple one with just two springs to center the humeral head. And this is the model from Menze with a lot of spring you can see in red. The kinematic is really close to physiological kinematic with humeral head translation, but all the load like the effort to center the humeral head is made by the spring, not by the cuff muscle. So it's good for the kinematic, but not so good for the physiological activation. So the first objective was to develop a 5 degrees of freedom shoulder model with physiological activation of the cuff muscle. To answer the question, how does the critical shoulder angle variation affect the biomechanic of the joint in a musculoskeletal shoulder model with humeral head displacement? And the main hypothesis was that by releasing degrees of freedom, the cuff muscle activation will increase in order to stabilize the joint. We also hypothesize that a large CSA will have a higher instability and therefore high activation from the cuff muscle. And this hypothesis come from the MORE study I've presented at the beginning of the presentation. So the shoulder model I use is the one from anybody. So we have 118 fiber muscle that come from it's a heel type muscle. And for each fiber, like most fibers, we have individual wrapping objects. The parameter for the bone geometry come from the Dutch shoulder group. And I use the scapulo-humeral rhythm proposed, so it comes from the equation of de Groot. I've made some additional modification in order to improve the moment arm of the muscle. I had supraspinatus torus object to really help the supraspinatus to wrap properly around the humeral head. And I've corrected the subscapularis insertion position, so it's really fit into the lesser humeral tuberosity. And in terms of so what I've been doing in order to have humeral head translation is that I remove the ball and socket joint, and I've implemented both methods I've presented earlier. So the Elabashi sphere and sphere model with the FDK. So we have a small sphere that is for the humeral head and a larger sphere that is for the glenoid of the scapula. The ranges come from our statistical shape models, so it's like the mean of the radius that we have observed at the CHUM hospital. And I've connected them both with a connected rod, so this constraint you can see over there. And I use the FDK solver in order to constrain the humeral head position and to compute it across the motion. So you can see over there the humeral head, so the blue spheres that can move into the glenoid, and because of the geometrical constraint, it remains in contact. The black arrow is the joint reaction force, so it really stays into the glenoid, but it's just like the position of the humeral joint is an output of the static equilibrium. So it's really the cuff muscle that will help to achieve this motion and not any additional spring. So in order to simulate different CSA, we've moved the insertion of the lateral deltoid. So I've represented a small CSA over here, a normal CSA over here, and a large one. And we simulated an overhead, an over-shoulder movement, so abduction in the scapular plane up to 130 degrees. And we investigate the output, so the humeral head displacement, the muscle forces, and the resultant forces. We consider the instability ratio, which is the ratio between the shear forces and the compression forces. So in the first phase of the movement, we can see that with a large CSA, there is more displacement of the humeral head in the superior direction. This can be explained by the line of action of the deltoid, which is really more vertical and pulls the humeral head upwards. And the order of magnitude is consistent with the range of displacement that has been found in the literature. So you can see like the dots on the graph here. After 60 degrees, the deltoid no longer wraps around the humeral head, so we can see there. Here. And its line of action is pointing toward the glenoid. So therefore, there is no longer destabilization of the joint. And as we saw earlier, some cuff muscle generate more forces to lower the humeral head in the second phase of the movement. So the humeral head is centered into the glenoid and no displacement occurs. Which explain like the near zero translation we have at the end. So now if we look at the forces generated by the muscle, we can see on the one hand that the deltoid produce less forces with a large CSA. It's also true for the supraspinatus. But like the other muscles, so the deltoid anterior and posterior, and the other cuff muscles, so the infraspinatus and the subscapularis, produce really more forces at the end of the motion. So if we compare to what we saw just before with the humeral head displacement, at the beginning of the motion, the deltoid really pull upward and destabilize the joint, so we have more humeral head translation. But at the end of the motion, the cuff muscle activate more, and they really help to center the humeral head. And this effect of the cuff muscle and anterior posterior deltoid have been also investigated in the literature. The supraspinatus is really active at the beginning of the motion. It's the first abductor in the first degrees of elevation, so that's also consistent with the literature. So now, if we're interested in the stability, the instability ratio, which is like the ratio between shear forces and compression forces, we observe the same thing. So with a small CSA, it's really it's more stable. And like the effect is really only at the beginning of the movement, so before 60 degrees. With a higher CSA, the deltoid really pulls the humerus upward. We have more humeral head displacement, and the instability ratio is higher because it generates more shear forces. This instability ratio has been observed also in the literature with cadaver study. And this effect of the CSA have been observed. So with normal CSA have a lower instability ratio that higher CSA with rotator cuff tear. So to sum up this part, what we can see is like with a low CS, like increasing the CSA in the first part of the abduction leads to an increase of the instability ratio, decrease of the abductors, and an increase of the displacement of the humeral head. And this increase of the humeral head can lead to impingement syndrome, so that the supraspinatus tendon can be pinched between the humeral head and the acromion. After 60 degrees, so we observe a higher load of compression at the beginning of the movement with a small CSA. A decrease of the lateral deltoid forces, but an increase of muscles that stabilize, so infraspinatus, subscapularis, but also interior and posterior deltoid. So with a small CSA, because of the compression forces, there is a risk, like it's over compression. And like this increase of the muscle can lead to an overload of the cuff muscle, or if they not succeed to center the humeral head, there can be a risk of joint dislocation. So we find the same consequences as more study, that a small CSA can be at risk of osteoarthrosis because of the increase of the compression forces, and that a high CSA, so above 38 degrees, can be at risk at the rotator cuff tear, either with impingement syndrome, overload of the muscle, or joint dislocation. So to our knowledge, it's the first time that a sphere-of-sphere representation of the glenohumeral joint is used to assess the impact of the CSA variation on muscle forces and on the joint reaction forces. It provides a mechanical explanation for the relationship between morphology and pathology. So this study has been published on Journal of Biomechanics if you want more details, and the model is also available on GitHub. So now I will talk briefly about the second studies I've been conducted. So after the morphology, I was really interested in the rotator cuff tear specifically. And what I found in the literature is there is like muscle compensation that can happen after a muscle is torn, but there is there is a lot of heterogeneity in the studies. So compensation have been observed by the deltoids, the biceps, some like dorsi, trapeze, subscapularis, and some studies also found that even if they're torn, the infraspinatus and supraspinatus can activate. And all this variation in the study is mainly due because there is no homogeneous classification, and also it's only few studies with few subjects because of methodological challenges. For example, like to assess those variation, we need to have EMG on the cuff muscle, and it's intramuscular EMG, but the patient with RCT are really in pain, so there are just only very few studies. For me, the classification I will use, it's a Collins classification, so with 5 different types of RCT. So 2 with only 2 muscle tone, type A, which is interior superior tear, and type D, which is superior posterior tear. And all the 3 BCT have 3 muscle tone. And so the objective of this study was to assess the relevance of the sphere-on-sphere FDK model to study rotator cuff tear effect on the glenohumeral joint biomechanics. The research question was, does the RCT type, so depending on which muscle is torn, influence the stability of the glenohumeral joint? And the main hypothesis was like muscle with similar line of action will compensate for the muscles that are torn. And if we are in case of massive RCT, so at least 3 muscle torn, the joint will be really less stable. So in order to simulate those different tear, we use the sphere-of-sphere model, and we turn out the muscles. So for each type, we say that all the fiber of muscles that are torn, the maximum force is equal to 0. So we simulate an intact cuff and all the 5 type of Collins classification. And as before, we simulate abduction in the scapular plane up to 120 degrees. So the result, what we can see, so you have here in black the reference. So the reference with the intact cuff is really, really close to a ball and socket kinematic. So few translation, it's a bit superior at the beginning and inferior at the end of the motion, and it's more posterior. In terms of types, rotator cuff type tear, so the type A, so the blue one over there, is the closest to the intact kinematic cuff. It's only like the supraspinatus and the superior part of the subscapularis that is torn. The red over there, it's type B, so it's the other one that have only two muscle. It's the other one that is a bit more stable, so around 5 millimeters of translation. And all the others, so type B, C, and E, have a really high superior translation, over 6 millimeters. If now we look into the instability ratio, so as expected, so the reference, the cuff will activate well, and it's very stable, so close to a ball and socket joint, only a very low instability ratio, so a lot of compression. The blue one, so the one that was closer to the reference, have also a low instability ratio. And what we can see is like the three over there, so type B, C, and E, that have 3 muscle tone, have a very, very high instability ratio. It's above 1. So what that means is like there is not enough compression forces to center the joint, and so they're a very high risk of dislocation. And now if we compare the muscle forces, so I've been only looking, I'll be only presenting between 30 and 60 degrees because this is the highest instability range. We can see like for all different muscles, the deltoid activates really more than the reference. So there is in every case a compensation from the deltoid, but this compensation is really higher for like type B, C, and E. So the type where there is like, it's a massive rotator cuff tear. And in terms of cuff muscle, the compensation really depends of the type of tear. So we can see type A, which was the most stable, have a very good compensation from the infraspinatus. It's higher than the reference one, and also a very, very important compensation from the lower subscapularis. Type D, that was less stable than type A, but still no dislocation, have a compensation from the upper subscapularis and the teres minor. But on the other end, so the 3 others that are very not stable, type B, C, D, and E, even if the muscles are not torn, for example, the upper part of the subscapularis or the lower part of the subscapularis, there is no compensation. So it's only the deltoid, and that explains that the abduction can be performed, but there is a high risk of dislocation because there is no, like the cuff muscle does not activate to center the joint. So to sum up, the deltoid activity increase from every tier. The cuff compensation is really tier specific. Type A is the most stable and has the most efficient compensatory response, and massive RCT don't achieve stability at all. So the deltoid will constantly increase forces in order to preserve abduction and produce the torque. But compensatory recruitment remain cuff and scapular muscle, it's tier specific according to Collins classification. This, if you want more details, this studies has been submitted to Journal of Biomechanics, and it's currently only, it's under review, but the preprint is available. And so the next step for me will be to assess both scapular and humerus morphology on the shoulder stability in case of RCT. So the first study was only focusing on the scapular morphology, but the joint is 2 articulations. So I think it's also very important to consider the humerus morphology, and we can do it by assessing the effect of the greater tuberosity angle, which is also a radiological parameter that is used in clinic to predict rotator cuff tear. And so I will do it, I will combine like see the effect of CSA and GTA in case of curve tape. And to do that, I have like CT scan from patient from the CHUM hospital, and I will personalize the model to the 6 patients that have variation of CSA and GTA and see the effect of the biomechanics. And finally, I will assess the limit of the model. So I think the main limit is the validation. Even if we find same, like for the first study, same results that have been found in cadaver, proper validation is really needed. And it could be done by validating the kinematic of the humeral head translation, by comparing the kinematic simulated by the model to kinematics that could be recorded in vivo. We have kinematic from intracortical pin, and so that could be a next step and an important step toward validation. Also, in this model, soft tissues are not represented, so there is no labrum, there is no ligament. And I think like combining the spherosphere model with the work Joanna Menze have been doing on the shoulder model could be an important step too. And finally, I've been only looking for scapuloplane abduction, but it's very important to consider real types of movements such as daily life activities. And another very important step would be to test the model with different movements, especially daily life activity and not like very simple and basic movement. So thank you everyone for your attention, and I'll be glad to answer any question.
Thank you, Margaux, for this amazing presentation. By the way, Margaux will be finishing her PhD this year, and you should absolutely get in touch with her if you think she can add value to your team or would like to collaborate with her. Just before we go to the Q&A session, I'd like to say a few words about our online resources and upcoming events. If you want to know more about Anybody Technology, you can go and check out our website, anybodytech.com, where you can find different events, special dates, and previous webcasts. You can also check out anyscript.org, which is our community website for people using Anybody. Here you will find multiple online resources such as our wiki page, several blog posts, and links to the repository sites. Our forum is also located on anyscript.org, and here you can ask questions and get help from some fellow Anybody users. We also have some upcoming events that I would like to highlight. On February 11 and 12, we are hosting Anybody Solutions Days, where you can book a 30-minute online meeting and get support from one of our engineers. Then there is a PhD course on musculoskeletal modeling at Aalborg University in March. I would highly recommend the course to beginners in musculoskeletal modeling. Finally, Anybody Technology will be present at ORS 2026 in USA from March 27 to 31. You are welcome to visit us if you're going to be there. To end this presentation, I would like to mention that we maintain a publication list of papers using Anybody modeling system and a library of previous webcasts. These are great resources if you want to get inspiration on how to use Anybody. This brings us to the Q&A session, and we will read some of the questions from the audience. Morten, I believe you have had some time to look at the questions. Can you take up the first question?
Yeah, no problem. So one of the questions that I've gotten in is for you, Marco, is how have you assessed the sensitivity of the model to, for example, the radii of the different spheres? So maybe you can elaborate a little bit on that.
Yeah, so I think I've got, before like running the test, we assessed like if the radius of the sphere have an impact of the on the output, on the muscle forces and instability ratio. It's actually like the whole study is on the first paper. And so you can see over there, it's a ball and socket joint, so just one, the ratio between the two radius, and it gets lower with a darker one. And so what you can see is like if you have a ball second joint, you have a higher force of the deltoid, and so yeah, you have a higher force of the deltoid, and like the subscapularis muscle and other cuff muscle really increase. So it's really at the beginning of the abduction, but like infraspinatus and subscapularis forces increase if you decrease the like it really like with a lower congruence, you have higher forces of the cuff muscle and a lower of the deltoid. And in terms of instability ratio, it's also the same. Like you have a higher instability ratio with a lower congruence, which makes sense. Like if the humeral head has more space to move into the glenoid, it's less stable.
Another question that we got in here is somebody is asking if it was indeed available on GitHub, and I think I can tell that it is, because I helped you put it on our GitHub page, so everyone can find it in there. There's also many other good resources on GitHub. The newest model repository, for example, in a beta version, is available in there that has some nice additions to the trunk model and stuff like that. But this question here, who asked about GitHub, has a follow-up question. So they are asking if you account for the size of the muscles in any of your modeling approaches, for example, to account for degeneration and atrophy.
I didn't look like for the size of the muscle. I've been doing some tests where I was like reducing the maximum forces that the muscle can produce. But like the size, no, it's really difficult to personalize properly the muscle geometry. And so I've been sticking to the heel type muscles that is proposed directly on the IMMR.
And why did you choose to study the abduction up to 120, 130? Was the model still stable beyond 130 degrees? What was your experience on this?
After 120, 30, I have like the subacromial distance is very low, and I have a conflict. I think it's because I should personalize scapular humeral rhythm, so it really moves more. So I can like it's stable up to 130. After that, I have penetration of the humerus into the scapula. But I think like personalizing the scapulohumeral rhythm will really help with this problem.
Thank you, Margaux. I have one more question that I would like to ask you again. This is from the audience. Your results show that the instability ratio decreases abruptly in the late abduction phase, even below the reference. What is your opinion on this?
I think it's because of the objective functions that I'm using that really want to minimize the sum of the muscles. So the cuff, like the solution of the FDK to have like the more stable position is really low. So if we look to, we also have like inferior translation. And this last part is really for me due to the choice of the objective function that will really look for the position where it's the most stable and it's a bit below what has been observed in the literature. So yeah, it should be like I didn't have so many time to do it, but like by playing with the objective function, I think we can like have a good compromise to have like a good stability, but it's not too much.
Thank you, Margaux. Morten, do you want to ask the next question?
Yeah, no problem. So we got a question here, Marco, which reads on slide 21. How did you define the measure, or how do you define or measure the translation? The figure on this slide shows the contact center of pressure, or does it show the contact center of pressure or the translation? I think that's the question.
It's not contact pressure, it's a translation. And the translation is measured between like the center of the glenoid on the scapulohumeral reference frame, so GH, the GH frame of the scapula. and the center of the humeral head. So it's really like the distance between the center of the two spheres. So it's the difference between like the reference frame on this point and the reference on this point. So as the humeral head moves, we have the humeral head position into this reference frame.
Margaux, were you just to interrupt? Were you showing something on your screen? Because maybe I will make you the presenter again. So.
Oh, okay. I thought I was presenting. Sorry.
I will just make you the presenter again.
Okay. So how I calculate humeral translation is I calculate the position of the humeral head, so the center of this sphere, in the ref frame of the glenoid sphere, so this one. So the humeral head translation is really the humerus in the ref frame of the scapula. So yeah, I think that answers the question. And like the other slides, so it was 21. It does not show contact forces, but really the humeral head position. So like the translation.
Thank you, Margaux. We are getting a few questions, but I think we are also running short of time. So we'll take up the last question for now, and then I think we'll get back to you on email for the questions that are still not answered. So the last question is, have you checked the continuity of the muscle moment arm curves against time?
Yes.
Have you validated those muscle moment arms, especially for the muscles surrounding the GH joint?
Yeah. I've been looking into the moment arm, and I also like it's always continuous. And I've been like all the adjustment I've been doing at the beginning. So the additional torus the additional torus and the adjustment of the subscapularis insertion position was to have moment halves of the muscles that are continuous and that are in range of the one I found in the literature.
Thank you so much, Margaux. I think maybe there are still a few questions, but we're running short of time, so we will stop here, and we will get back to you for the questions that have not been answered yet. So we'll reach out to some of you on email, and we'll Margaux or we will try to answer these questions. So I'd like to just thank you, Margaux, for this amazing presentation and for your time today, and also to our attendees for making this an interesting session and asking these great questions. So thank you so much for your attendance, and we'll see you in the next webinar. Have a nice day.